Hello everyone, welcome to Vedanta JEE English channel. This is your Big B and physics coach Madhan sir. If I am audible, if I am visible, just say clear. We will start the session. Today we are going to be doing heat transfer. By the way, how you people are doing? I'm doing great. How are you people doing? Just comment. I'll see. If you can hear me and if you can see me, please type in clear. If you can hear me, if you can see me, please type in clear. We will start with the session. Please type in clear. We will start with the session. Please type in clear. We will start with the session. Good evening. Good evening, Diviteja. Good evening, BTS Army. Hi. Sultana. Hi. Okay. So, leaving ray optics and surface tension for JEE mains, will it affect for JEE advance? I didn't get you, man. See, ray optics, I don't know for what reason you want to leave. Ray optics is easier. If you put some efforts, ray optics is easier. And surface tension also, if learned from a proper teacher or from a proper, I won't say there is no proper book. If learned from a proper teacher, then surface tension is also easier. Yes, if you are going to ask me that will it affect? Yes, it is going to affect for JEE advance. Yes, it is going to affect for JEE advance because ray optics is deemed scoring by majority of the students. Majority of the students feel that ray optics is scoring. Surface tension might be a bit difficult, but ray optics they feel it to be what we call scoring topic. So type in hi ISRO IIT Guwahati. Good evening everyone. Come on, please say clear. If you say clear, we'll start with the lecture. If you people say clear, we'll start with the lecture. Please say clear if you can hear me and if you can see me. So, if you can hear me and if you can see me, please say clear. If I get that confirmation, I can go ahead. Okay. So, there is a crash course which is going on where majority of the people have enrolled. So, please don't miss the bus, right? The thing is, in crash course, you are going to have a scheduled classes, a proper timetable that this week this will be done, this week this will be done. So you will have proper targets, and then every week you are going to test your knowledge on those chapters by writing an examination. So all those things are going to be provided to you in this crash course. If you people can afford to buy it, do buy it. If you people can afford, please buy it. Okay, now. Okay, now we are going to do heat transfer. So if I am going to talk about the modes of heat transfer, there are three modes of heat transfer, right? Out of which two modes of heat transfer require medium and one mode doesn't require medium, and that mode which doesn't require medium is going to be called as radiation. So radiation doesn't require medium to travel from one location to the other location, but if we talk about the other modes, they do definitely need medium. So out of which conduction is one such thing where heat is going to be traveling from one location to the other location without the transfer of medium. So basically conduction, if we talk about conduction, requires medium. It requires medium, and what will happen? Heat gets transferred without transportation of medium. Without transportation of medium, heat gets transported. Heat gets transported. One best example is going to be, let's say you are doing cooking. when you are going to be doing cooking, one of the utensils is going to be there on the gas stove, right? The utensil is going to get heated up, and then you are going to have some one more rod kind of thing or something which is used for stirring purposes, right? Let's say for example we have a spoon and we are using the spoon to stir the material which is getting cooked. So if you keep the spoon for long duration, you will feel that the spoon has got hotter, and you feel that some heat is reaching your hand. So in that way, if you look at, heat is reaching from the stove to your hand, but the material hasn't moved. So whatever the spoon you are holding on to, the material of the spoon didn't come to your hand, but heat has come to your hand. That's a clear indication that medium didn't get transported, but heat has got transported. So when there will be heat transfer in all these, in these situations, there should be a temperature difference. If temperature difference is there, then definitely there will be heat traveling from one temperature to the other temperature. In fact, higher temperature to the lower temperature. Yes, we have one more mode called as convection. So what is this? This is something which requires medium. This requires medium. So how different is convection from conduction? See, in conduction, medium won't get transported, but heat get transported. In convection, medium along with the heat gets transported. Medium gets heated, medium gets heated and transports heat along with it. So if we are going to talk about convection, what is the weightage of convection in competitive examination? You can say almost zero. Barely there can be any questions asked on this. Whatever are possible, I'll cover it up in 5 to 10 minutes. So convection is going to be 5 to 10 minutes in this class. And then radiation. Radiation is something, is a mode of heat transfer, right? Doesn't require any medium. So that's how whatever the heat is generated at sun is reaching earth. In between there is nothing. In between there is nothing. It's free space. So doesn't require medium. Now if you talk about for competitive examinations, what I have seen is radiation is preferred a bit in JEE Advanced, but not in JEE Mains. Very rarely questions have come on radiation. But at the same time, if there is a question coming on radiation, you people should be able to attempt it, should be able to answer it. For that reason, I will not dig too deep. If it is on advanced level, alone radiation has to be taught for 2 to 3 hours. Alone radiation on advanced level with proper examples. But on mains level, as our ROAR series is mostly focused on to this mains thingy first, so this radiation I'll spend around 20 minutes of time to just explain what is radiation, what are the laws which are involved in it. That's it, right? Majority of the focus in this class will be on this, because this is the one where a lot of questions has been asked. So obviously we have to focus on the thing which is asked a lot. So conduction, I'll be spending roughly around 1.5 to 2 hours. You can say roughly 2 hours is going to be on conduction. So the whole lecture is going to be around 2.5 hours today. The whole lecture is going to be around 2.5 hours. Okay, fine. Now let us talk about conduction. There is actually a proper trend for conduction. There is a proper formula. Convection doesn't have that kind of formula. Radiation again has formula. So what does conduction say? Look, if you have a layer which is at some T temperature, and if I have one more layer which is at a distance of dx, and if that has a temperature T plus dt, then the amount of heat that is going to be crossing this one, the amount of heat that will be crossing this layer whose thickness is dx is the amount, rate of heat flow, sometimes also referred to as heat current, that rate of flow of heat is directly proportional to the area of cross section. Let us take this to be having an area of cross section A. So the dq by dt is directly proportional to the area of cross section, and the dq by dt, the rate at which heat is going to be flowing, is directly proportional to the temperature gradient. Man, whenever you are going to come across changes of something with respect to position, we call it as gradient. So here dt by dx, here we are talking about changes of temperature with respect to x, so temperature gradient. dt by dt, then it is going to be rate of change of temperature. dv by dt, rate of change of velocity with respect to time. So whenever we generally say rate of changes, it is with respect to time. Whenever we say gradient, it is with respect to position. So the rate of change of temperature with respect to position. Now if I put all of them together, then what am I going to get? I get minus a dt by dx. Now I will replace the proportionality with a constant, and that constant is k, called as thermal conductivity. So the rate of flow of heat through the material. Look, the rate of flow of heat through the material whose thickness is dx, whose area of cross section is a, and the temperature difference is dt, is this much, minus ka dt by dx, where k is thermal conductivity and it is a material property. Okay, fine. Now let us look at what exactly is going to happen. For example, what I'll do is I'll just take a rod. This is a rod at, let's say, 30 degrees Celsius. So every layer of it is at 30 degrees. Every layer of it is at 30 degrees. Every layer is at 30 degrees. Okay, fine. Now, Anil, good evening. Sanju, good evening. Okay, fine. Now, what I will do is that rod, whatever I am talking about, is going to be maintained across some hot reservoir and cold reservoir. This is called hot reservoir, and this is called as cold reservoir. See, what are these reservoirs? Man, have you ever been to a reservoir? Reservoir is something which is going to store lot of water with it. Now, let's say you carry some 1 liter bottle with you, right? You go to the reservoir, and with the 1 liter water bottle, you just take 1 liter of water from the reservoir and take it out. Will the level of liquid fall in the reservoir? No, more or less it will be same. By taking out 1 liter of water from the reservoir, or by giving 1 liter of water to the reservoir, level of the water in the reservoir is barely affected. So what is the meaning of hot reservoir and cold reservoir? Man, we can see this is going to be having higher temperature and this is going to be having lower temperature. As there is temperature difference, we have a medium, then there will be heat which is going to be flowing through this rod. So that means hot reservoir is going to lose heat and the cold reservoir is going to gain heat. Right? Now, what we have seen in the previous class is that if a body is going to lose heat, it will cool down. If a body is going to gain heat, it will become hotter. So this one is losing heat, so this should cool down. But as I said it to be a reservoir, the quantity of heat given away by this reservoir will barely affect the temperature of this reservoir. How you are going to be comparing? For example, if you take 1 liter of water from the water reservoir, the level of the water will not change much. In the same way, if I remove certain amount of heat from this reservoir, the temperature of that reservoir doesn't change. So basically, by giving you the reservoirs, they are trying to say that temperature here constant, temperature here constant. So as there is temperature difference between the ends of the rod, so through the rod some heat is definitely going to flow, right? Now what happens is that when heat enters from this hot reservoir to the rod, layers of the rod get some heat. Let's say they got some 100, some 10 or 15 they'll transfer 80 to the other one. So in the beginning, in the beginning some of the heat is retained by layers and they change the temperature. But after some time, temperature of layers remains constant and that state is called steady state. That state is called steady state. So in the beginning, yes, the whole rod, every layer of it, let's say, was at some 30 degrees. So in the beginning, when the heat is flowing, some heat will be taken by the layers and they change their temperature. And that process keeps happening only till certain point of time. After certain point of time, temperature of the layers will not change. And once that state is going to be attained, we call it as steady state. So in order for you to understand even in a better way, for example, let us take this to be 100 degrees Celsius and let us take this to be, let's say, some 40 degrees Celsius. Then at steady state, what is going to happen is what I am writing. At steady state, what is going to happen? That is what I am writing over here. Look, let us pick a layer, this layer. Let's say this layer is having some 70 degrees Celsius and it will remain to be 70. It will remain as 70 degrees forever. That is what is called as a steady state. Now, if I am going to talk about, let's say the layer over here, as the layer is going to be going closer to the hotter one, its temperature will be more. For example, let us take the temperature of this to be 85 degrees. It will remain as 85 degrees forever. That is what is called as a steady state. That is what is called as a steady state. Okay, Anna trick. The class is going to be getting over around 8 o'clock. Around 8. Okay, fine. Now look. You take me to be the layer which is at 85. How much our heat I am going to get? I have to give away the same amount of heat. Why? If I retain some heat, my temperature should change. Let's say I'm getting 100, I have to give away 100, otherwise my temperature will increase. If I'm getting 100, if I give 40, I'm keeping 60, my temperature should change. But that is not happening at steady state. If I get 100, I'm giving away 100. So whatever the 100 I got, I give to the next layer. Then the next layer is getting 100. Even that layer is not changing its temperature. So whatever the 100 it got, it will give away the 100 to the third layer. Then the third layer gets 100, and it should also give away 100, because at steady state no layer is changing its temperature. That means how much our heat is crossing this layer, the same heat has to cross this layer. So at steady state heat crossing every layer is constant. So at steady state, I can claim that dq by dt is constant. So this is one important result which you people should keep in mind. This happens only at steady state. And sir, once the temperatures have attained constant values for the layers, we call it steady state. When the temperatures are changing, what is that called as? It is called as transient state. Okay, fine. Now look, and you might have it out, sir, this formula whatever you have given, is this formula valid for steady state, or is this formula valid at any point of time? This formula is valid at any point of time, whether the temperatures are changing, whether the temperatures are not changing at an instant. If the left side is having T temperature, if the right side is having T plus dt temperature, then the amount of heat crossing is always given by this, whether it is steady state or whether it is transient state. You don't need to worry. So this formula is universal kind of thing. Okay, I have given you better conceptual clarity. Now look, let us go for the standard results. For example, I have a rod, and the thickness of the rod, or you can say length of the rod, I am taking it to be L, and the thermal conductivity of it, I am taking it to be K, and the area of cross section, I am taking it to be some A. Now the left end is maintained at TH, which is the higher temperature, and the right end is maintained at TC. Now I want to talk about how much heat is flowing from the hot reservoir to the cold reservoir, right? So for that, what I will do is I'll just look at a distance x, I will talk about a layer which is some dx thick, right? So if I am going to take the temperature here to be T and the temperature here to be some T plus dt, I know how much heat is crossing that. We have a formula. So what is that dq by dt? That dq by dt is minus ka dt by dx. Okay, nice, good. Rate of heat flow. Now man, I want to calculate this dq by dt. So what I will do is dq by dt into dx is minus ka dt. I want to do integration because from dx I want to get length. From dt's I want to get temperatures. TH and TC have to be related. So from dx, if I have to get L, I need to first get dx. Sorry, first x integration. And for your kind information, at steady state, this one is constant. As this one is constant, a constant can be taken out of the integral. Yes, let us take it out. Let us take it out. Otherwise, I couldn't have taken, man. Very important. Otherwise, I couldn't have taken. So it would have been integral dx is minus ka integral dt. Now look, x is measured from the left hand. At x is equal to 0, what is the temperature? TH. At x is equal to capital L, what is the temperature? TC. Right? So what is integral dx? X. Now dq by dt is going to be integral dx is x. So after substituting the limits, you get L minus ka. Integral dt will be what? T, which is going to be what? Tc minus th. So if you put the minus sign, it will become th minus tc. Then the dq by dt rate of heat flow is ka, higher temperature minus lower temperature, or you can say cold temperature or cold reservoir temperature is this. And sometimes this rate of heat flow will also be called as heat current, because rate of flow of charge is electric current, rate of flow of heat is heat current. So sometimes dq by dt will also be written as capital H is going to be what? Ka, higher temperature minus the colder temperature divided by L. My suggestion to you is you keep this in mind. You keep this in mind. Now, Sumesh is asking a question. Is Engage good book for modern physics and thermodynamics? Yes, ma'am. It's good enough. It's good enough. Okay. Now, let us go back. Let us start dealing with this. I know dq by dt, right? Now, I want to calculate temperature at x distance. Temperature at x distance. The left end is maintained at TH, the right end is maintained at TC. So the layer which is in contact with the hot reservoir will have TH. The layer which is in contact with the cold reservoir will have its temperature as TC. But now what I want is the temperature of a layer which is at X distance. Let us take the temperature over there to be some T. Let us take the temperature over there to be some T. Okay. Now, one thing which you people should know is that I can treat this whole thing as one rod. I can treat this whole thing as one more rod, and you can say same amount of heat will flow through both of them. So I can write the dq by dt here as K a higher temperature minus the lower temperature divided by x. Again, if you look at this section of the rod, this end is maintained at T, this end is maintained at TC. So Ka T minus TC divided by capital L minus X is the length of it. So Ka. And how I was able to equate them? How much our heat will flow through this one? Same has to flow through this one at steady state. Okay, fine. Now you only tell me, what are you going to get? What are you going to get by solving this? Our aim is to calculate the T value. That is the temperature at x distance. So L minus x into TH minus T is going to be x into T minus TC. So when you do the math, it's LTH minus LT XTH plus XT is XT minus XTC. So XT gets cancelled out, and if you are going to look at what will be the temperature, see this is going to go to that side, right? So what is that you are going to get? You get this side, which is going to be L plus this, and this gets kicked out. Our aim is to calculate T, take all the T's onto one side and rest of the things onto the other side. So you get LTH minus XTH. So basically I can write L minus X into TH, right, minus X into TC is going to be LT. So from here, what is the T value? The T value is going to be L minus X by L into TH minus X by L into TC. This is what you get. Yes. This is what you are going to get. If you want to simplify it further, which is going to look bit better, so you can write it as minus X by L into TH minus TC. This is how the temperature will be, man. So if you are moving from this end, that's how the temperature is going to be. That's how the TH value, TH minus X by L into TH minus TC. So now look, if you observe it properly, T is TH minus TC by L into X. So if I am going to be plotting a graph between T and X, what will be the graph? It should be a straight line with positive slope. Why? Whatever will be plotted on y-axis, you write it as y. So I am going to plot temperature on the y-axis. TH is the constant plus mx, but keep in mind the slope is negative. Slope is negative. So how the temperature is going to be varying? How the temperature is going to be varying? If I plot a graph with the temperature on this and with x on this, then what is the type of graph you are going to get? Y is equal to mx plus c. So it's a straight line with negative slope. So we have, what is the temperature here? We have TH and we have TC. That's it. So this end is the TC temperature, this end is the TH temperature, and rest of the layers have temperature between TH and TC. Good boy, Vishal. Hi. Hi, man. So this is how the temperature is going to be varying. In fact, the temperature is varying linearly. So let me give you one small question. We have a rod. This end is maintained at 100 degrees and this end is maintained at 0 degrees. Let us take the length of the rod to be 2 meters, right? I want the temperature I want the temperature at half meter. We have a layer which is at half meter and I need you to find the temperature over there. All we know is that the temperature will be decreasing linearly. With how much slope? The negative slope is Th minus Tc by L. So, if you are going to be moving 2 meters, what will be the change in temperature? For 2 meter movement, change in temperature is 100. Then for half meter, what will be the change in temperature? So the question mark is going to be this into this into this, which is going to be half into 100 divided by 2, which will result in what? 25. So the change in temperature should be 25. How I know that? How I know that I have to use this? See, this can be used only when the variation is going to be linear. And how I know that it is linear? I proved it. It is going to be like a straight line. The variation is going to be like a straight line. Either you can blindly use this formula, but generally it is a bit difficult for you to memorize the formulas. That's why I'm giving you this trick. Okay, fine. Now I know that change should be 25. And when you go like this, the temperature should decrease. Should decrease by how much? 25. Then the temperature, the actual temperature, 100 minus 25, which is going to be 75 degrees. Which is going to be 75 degrees. Okay. Do this question. And one more thing. In this question, there is a word called as energy flux. And look here. All the units are watt per meter square. That means power per unit area. So, from the options, I can realize that the energy flux we are talking about is going to be power per unit area. Power is nothing but rate of flow of energy. Who is going to flow over here? The flow is going to be heat energy. So rate of flow of heat energy per unit area is called as energy flux. Now you try solving this question. A heat source at 10 to the power 3 K is connected to another heat reservoir at 10 to the power 2 Kelvin by a copper slab which is 1 meter thick. That means its thickness, or you can say the length, is 1 meter. Given that the thermal conductivity of copper is 0.1 watt per Kelvin per meter, the energy flux, man, dq by dt can be written as what? Ka, higher temperature minus the colder temperature divided by L divided by area. So the area gets cancelled out. So it is going to be simply K into TH minus TC divided by L. So what is the K thermal conductivity? 0.1. Higher temperature 1000 minus 100 divided by, what is the length? 1. So 1000 minus 100 will be 900. 900 into 0.1 will be how much? 90. So the answer is going to be 90 watt per meter square. This is a simple formula based application one. Rook, this was asked in 2019. I will not be picking 2023, 2024 questions because they are generally bit on easier side. Most of the questions I'll pick on 2019 and 2020 questions. 2020 is the best JEE main shift that has been conducted and the questions are super tough when compared with all the shifts of JEE mains. So if you ever want to talk about how many marks you people are going to be getting in tough papers, you can sit and do the papers of 2020. You will get a proper idea. Okay. So this is a simple formula application one. Now, what I want to do is, I just want to extend and give you one more question. I just want to give you one more question. Let us take this rod is going to be, let us take this rod, let's say, is at 30 degrees Celsius. Is at 30 degrees Celsius. Now that rod, whatever I am talking about, is maintained, let us say, at T1 temperature on this side and a T2 temperature on this side, right? So a steady state will be attained and heat will be flowing. Now, by the time, okay, for easier calculations, take T1 to be 100 and take T2 to be 0 degrees. By the time rod attains steady state, find heat absorbed by the rod. That means all the layers were at 30. Now, because you maintain 100 and 0, so this layer will have 100, 90, 80, 70, 50, 60, 50, 40, 30, 20, 10, 0. So the temperature of the layers have changed by the time it has reached steady state. That means some heat has been absorbed by the rod. How much heat is absorbed by the rod? How much amount of heat is absorbed by the rod? Generally, this question is deemed difficult. I have seen lot of students to struggle with this thing has to have, like, you people should have some amount of clarity on the heat chapter which we have done in the previous class, right? Now look, let us compare the old situation with the new situation. Let us compare the old situation with the new situation. See, if I am going to talk about a layer, if I am going to talk about a layer which is at x distance, more or less the layer which is at x distance whose thickness is dx, more or less initially all the layers are at 30 degrees Celsius. Now what happened? Once they reach steady state, once they are going to be reaching steady state, obviously, if you talk about temperature at x distance, the temperature of this one is going to be higher temperature, which is 100, minus higher minus the colder divided by the length into x. So you get the temperature here to be 100 minus 100 x by L. So which is going to be 100 into 1 minus x by L. So what happened, man? So this section, whatever I am talking about, previously was at 30 degrees. Now is at this much. Now it is at this much. So obviously the temperature has changed. That means this has absorbed heat. It has taken heat. How much heat it has taken? We know the formula. Delta Q is going to be ms delta T. This is the formula which we have learned from the previous chapter. So the heat, the small amount of heat absorbed by this one is going to be the dq, small amount of heat. Obviously, small mass is absorbing it. S into delta T. What is delta T? The temperature minus the 30 degrees. Finally, it is at this temperature. Initially, it is at 30. Now, I need to know the mass of it. How to get the mass of it? The mass of it is density, volume, area of cross section into length. So, what is the length of that element? Dx. Area of cross section, I took it to be A. Oh, Sanjay. Welcome, man. I was waiting for you. So T minus this thing. So you have 100 minus 100x by L minus 30, which is going to be 100 minus. So 100 minus 100x by L minus 30. So the small amount of heat absorbed by the layer which is at x distance is going to be given by rho as 70 dx minus rho as by L into 100 x dx. Okay, this is the small amount of heat absorbed by this layer. Like that, we have many layers, na? We have to find out how much all the layers have absorbed. How much all the layers have absorbed. Okay. So if I want all the layers, how much they have absorbed, I need to integrate from where to where? 0 to capital L. 0 to capital L. If I do integration from 0 to capital L, I am talking about all the layers. So this is one good question. Okay. Rho as and 70 are constants. So 70 rho as are constants. Then dx. Integral dx will be what? X. Where to where? 0 to L minus rho as by L into 100 is a constant. Integration of x will be what? X square by 2, which is going to be what? Again 0 to L. Now what you will have? See, you are going to have L square by 2 and 100 by 2, 50. You have 70. So you have 70 rho ASL minus 50 rho ASL, which will result in how much? 20 rho ASL. This much heat is absorbed by the rod to reach steady state. To reach steady state. I said to you, right? In the beginning, all the layers are at 30 degrees Celsius. The beginning, all of them are at 30 degrees Celsius. To attain steady state, they absorb some heat and reach steady state. How much they absorb? This much. So this is a good question. This is a good question. Keep in mind. Now, we have to go for the comparison, man. Generally, in all the coachings, they are going to do heat transfer after current electricity. Why? Current electricity and heat transfer work in the same way. Current electricity and heat transfer work in the same way. So let me do the comparison. Let me do the comparison. Right? So if I am going to talk about current electricity, if I am going to talk about the current electricity, and on the other side, if I am going to talk about conduction, not even heat transfer, we are talking about conduction. Okay. Now look, in current electricity, we will have some resistance. Across that resistor, if I maintain some potential difference, then because of this potential difference, there will be a current which is going to be flowing. So the potential difference is equal to IR. Then the electric current is going to be V by R. For better conceptual clarity, I'll put delta V. So the potential difference across the resistor is going to be I into R, or potential drop across the resistor is I into R. So I can be written as delta V by R. Who is responsible for current to flow through the resistor? It is the potential difference maintained across the resistor. Now look, if we talk about a rod, this is maintained at higher temperature, hot reservoir, cold reservoir. The amount of heat, rate of flow of heat, which is going to be written as capital H, which is going to be called as heat current. Rate of flow of charge, electric current. Rate of flow of heat, heat current. And what we have Ka, higher temperature minus colder temperature, or hot temperature by minus cold temperature by this. So I can write it like this. TH minus TC divided by L by KA. Now look, man, who is responsible for electric current? The potential difference. Who is responsible for heat current? Temperature difference. So the role of potential difference is played by temperature difference, and the role of electric current is played by heat current, and the role of electric resistance is played by L by Ka. So I am going to call this as thermal resistance. I am going to call this one as thermal resistance, right? So one more page of comparison. Let's do that. One more page of comparison. Let's do that, because I didn't do current electricity to you. So I want you to be on the same page of me. Now look, electric resistance was rho L by A, which can also be written as L by sigma A, where sigma is conductivity, rho is resistivity. Okay. Sanjay, are you there? Thermal resistance is L by Ka. So electrical conductivity played by thermal conductivity. Here, what is L and R? Man, look, L is the length current travels in a resistor. And what is the area? What should be taken as A? Area through which current enters or leaves. See, when I am going to say area through which current enters or leaves, that means current entering. There will be some area through which current enters, right? And there will be some area through which current leaves, right? Both of them should be same. If they are not same, then you have to go for integration. Sir, what do you mean? What I mean is, for example, if you take a resistor which is going to be like this, on this side also we have A area, on this side also we have A area, so no problem, resistance of this is given by rho L by A. But what if we have truncated cone? Then if you are going to be comparing the truncated cone, current enters through small area and current leaves through big area. Now we have a confusion. What should be taken as A? Because I have defined A is what? Area through which current enters or leaves. If both of them are same, only then I can put it. But here, current entering and current leaving are not through the same area. That's when you will be forced to go for integration. Why you will go? Because to use the rho L by A formula, area through which current enters or leaves should be what? Same. Then what I do is, I will take an element. If I take an element, what is the advantage you are going to have? If you look at this element, area through which current enters and area through which current leaves is going to be what? Same. At least I can use this formula. So to use this formula, area through which heat enters or heat leaves should be same in conduction. If they are different, how you have done in current electricity, same thing you have to do in conduction also. If the variable area of cross section questions are going to come, then the paper is difficult, and mostly they are going to talk about truncated cones. I have a shortcut for this one. That's why I said to you, right, as I haven't done it, you should have my way of approach. Let us take the radius of curvature here, radius on this side is A and on this side is B. So when you have truncated cone like this, in the final formula, you just put the area as pi AB. This will do the required thing. So shortcut is whenever you have truncated cone, in the place of area, you just put pi AB, you will get the correct answer. So you don't need to do a lot of calculations. But I think I am very clear with how you have to be conceptually strong. How you have to be conceptually strong. So same thing is going to be happening here also. What is L? Length heat travels. Length heat travels. What is A? Area through which heat enters, area through which heat enters or leaves. So area through which heat entering and leaving should be same. If not same, then you have to go for elements and do the calculations. Clear everyone? Okay. Sir, applications are. Let us do it. Let us do it. What are the general questions we are going to come across in these things is that what we call finding the junction temperature, finding how much amount of heat is going to flow. These are the general questions we are going to come across. Junction temperature, like multiple rods are going to be joined. Keep one thing in mind. Whatever we have learned in current electricity are going to be valid here also. There, what is the junction law? How much our heat is going to be entering the junction, how much our electric current enters the junction, same electric current has to leave the junction. Here, how much our, how much our heat is going to be entering the junction, same has to leave the junction. So that's the reason why current electricity and heat transfer are not heat transfer. Current electricity and conduction are very similar. So if you learn current electricity, then you have conduction also in your pocket. That's how simple it is. So let us do some questions. Man, we have a thermal reservoir which is at some T1 temperature. We have a thermal reservoir which is at T2 temperature, and they are connected by two rods. Okay. So this rod is having K1 thermal conductivity, area A, length L. Now this one is having K2 thermal conductivity, area A, length L. What I want, find junction temperature and find heat current. See, to find junction temperature, one approach is going to be better, and to find heat current electricity approach is going to be better while solving the questions. Which part, Shiva Karthik? Which part you want me to explain? I'll explain again. I'm fine with it. See, whatever the thing I have done over here, you should have basic understanding of current electricity. If you haven't understood this, then you have problem with current electricity. Pragna is asking a question, sir, should I follow the chapter sequence? No, I won't suggest you to follow the chapter sequence, but I would suggest you to follow the easy chapter sequence. Sanjay K, is two metals are same coach? No. They are not same. You can clearly see the thermal conductivity is different. So they are different materials. Mr. Shivakarthik, if you can't respond, I can't help you. Okay, fine. They are different materials, man. If they are different materials, only then the thermal conductivities will be different, sir. Mr. Sanjay. Okay, fine. How do we solve this? So the solution. Look, this is at some T1 temperature. We have this rod. And then we have this rod. And this one, let's say, is maintained at T2. Let us take the temperature at the junction to be T. Rohit Kumar, it's fine. Pragya, I have done a video on that, like weightage of chapters and all those things. You just go through that. Or tomorrow also I'll be doing one video. You can attend that video if needed. Okay, fine. Now look, how much ever heat current is going to be going through this one, I'll write it as H1. Whatever the heat current is going through this one, I'll write it as H2. So how much ever is going to enter the junction, same has to leave the junction. That's the property. Now I can write H1 as what? I can write H1 as K1A higher temperature minus lower temperature divided by L. What about H2? H2 is going to be higher temperature. So K2 into A, higher temperature minus the colder temperature divided by L. So H1 should be equal to what? H2. As a result, when you equate them, A by L will get cancelled out. So I am skipping one step. So I am going to write K1 into T1 minus T is going to be K2 into T minus T2. As a result, the value of T will come out to be K1 T1 plus K2 T2 divided by K1 plus K2 is what you get. K1 T1 plus K2 T2 by K1 plus K2 is what you get. Okay, fine. Now look, we got the temperature of the junction. If I put the temperature of the junction in any one of those heat currents, will I get the answer or not? Yes. So, shit. Okay. So, as we already know that H1 and H2 are equal, okay, K1A into T1 minus the junction temperature. What is the junction temperature? K1 T1 plus K2 T2 by K1 plus K2 divided by L. Now do the LCM. If you are going to be doing LCM, what are you going to get? I think you are going to get K1 K2 into A T1 minus T2 by K1 plus K2 into L. This is the heat current you are going to get. And this is slightly lengthy process. For a heat current. Now, I want to do it in current electricity approach. I want to do it in current electricity approach. So let me give you that also. The current electricity approach, if I am going to talk about it, what is that? Look, this end is at T1 temperature, one rod. It is going to have some thermal resistance. How much is that? L by K1A. And the other rod is having how much thermal resistance? Other rod is also having R2 L by K2A. And here the temperature is T2. Done, man. What is the equivalent resistance? Because they are connected in series, right? As they are connected in series, what will be the R equivalent? It should be equal to R1 plus R2, which will turn out to be what? Which will turn out to be K1 plus K2 into L divided by K1 K2 into A. Now, if you want current, heat current is going to be what? The temperature difference, because that is the one which is going to play the role of voltage, divided by the resistance, which will turn out to be what? K1 K2 into A, T1 minus T2 divided by K1 plus K2 into L. Did we get it directly? Did we get the heat current directly? Spartan Kratos. Hi. Okay. We got it directly, right? Now, whenever we have to calculate the junction temperature, that's when we face slight difficulty with current electricity approach. Man, potential drop is equal to IR. So temperature drop should be equal to HR, because here H is heat current. So the temperature drop should be written as what? HR. So the temperature drop across R1 is going to be T1 minus T is going to be the heat current multiplied with R1 resistance. So from here you can calculate the junction temperature. From here you can calculate the junction temperature, right? So these are the two approaches. Now, just a second. Okay. Few more models on the very same thing. On the very same question, I would like to add one more. Man, we have two different materials. I didn't like it. We have two different materials and I didn't like it. I want to convert both those materials, replace both those materials with a single material. But what that material should do, it should not affect the amount of heat current that is going to flow. How much our heat current is flowing when these two materials are there, if I replace both those materials with a single material, same heat current has to flow. So that means I am talking about replacing this with one material which will have same thermal resistance. So look, if I should not affect the amount of heat that is going to be flowing, the total resistance should remain as it is. The equivalent resistance should remain as it is. That means those two bodies should be replaced with a single rod. Now, how much is the distance between these two reservoirs? It's 2L. So the material, whatever I am going to take, should have 2L length. So the rod which I am going to be taking, whose thermal conductivity is some K equivalent, should have same physical dimensions as both of them. So what is the R equivalent you get from here? The R equivalent you get from here is R1 plus R2, which is going to be L by K1A. R2 is going to be L by K2A, which in turn is going to come out to be K1 plus K2 into L divided by K1 K2 into A. And if you talk about the R equivalent here, what is the length of the rod? It is 2L divided by K equivalent into A. So how much our resistance is provided by these two rods together, this single rod should provide the same resistance. That's when we can say this single rod is equivalent to this rod. Now equate both of them. If you are going to be equating both of them, what will be the K equivalent? The K equivalent K1 is going to be 2K1 K2 by K1 plus K2. We have one letter 2 extra. Yes. Now, Spartan Kratos, if you already have some basic understanding, yes, it's worth listening. Otherwise, you can listen from YouTube. Whatever the chapters are going on in that, you can listen to YouTube and then write the tests and the DPPs. You can make your own DPPs, right? Make your own DPPs and write the tests which are happening in the weekend, such that you will have a target in front of your eyes. Mr. Spartan. Hey, keep your name, man. What is that Spartan nonsense? Keep your names. Look at Sanjay. Sanjay. It's good. Okay. Now, what if we have a parallel connection? What if we have a parallel connection? Look, I have this. I have one rod like this, whose radius is r. Whose radius is r. Better I'll do one thing. I'll just fill the color also. Ding, ding, and ding. We have one such thing like this. We have a rod like this. And now we also have one more like this. I'll talk about the dimensions of them. I will talk about the dimensions of them. I'm just praying to the God. Damn good. Super. Right? Look, I have maintained the left side one at T1 temperature. I have maintained the right side one at a T2 temperature. The radius of the blue one is R and the radius of the orange one is 2R, and both of them have a length L, and the thermal conductivity of this blue one is, the blue one has thermal conductivity K1 and the orange one has thermal conductivity K2. Find the heat current that is going to flow. Find the heat current that is going to flow. Find the K equivalent. So if I have to replace both the materials with a single material, what is the equivalent K? What is the equivalent K? Ajay Pranav. Refrigerator and Carnot's engine have been deleted. You don't need to prepare. You don't need to prepare on those things. Please don't focus on those things. Right? For JEE Advance, after the JEE mains first attempt, I will do Carnot's engine and refrigerator. And one more thing, man. Next week, I will be doing KTG and thermodynamics. Next week, I will be doing KTG and thermodynamics. And when I am going to be doing thermodynamics, I will not be doing Carnot's engine, any heat engine, Carnot's engine, refrigerator, all those things will not be done. Only first law of thermodynamics will be done, and to some extent, second law of thermodynamics will be done. That's it. Generally, they can't ask questions on second law of thermodynamics if we are not going to be dealing with heat engines. That's why last year there was not even a single question on second law of thermodynamics. Okay, fine. First of all, we have to talk about the heat current. But before we go for that, you should have a proper proper visualization of this question. So all those people who are going to be looking from the side view, so from the side view, how it is going to be looking like? How it is going to be looking like? From the side view, it looks like this. Right? This is how it looks like. This is how it looks like. Okay. Now, can you give me the resistance of that blue one, R1? So I'm going for the solution. Look, if I am going to talk about the resistance of the blue one, right, length L by thermal conductivity K1 multiplied with the area. Which area we have to take? Area through which heat enters and leaves. Luckily, through how much area heat enters. So this blue area, how much is the radius of it? R. Ayyo. This R and this R, you get confused. So what I'll do is, I'll change it to small r, man. I'll change it to small r. My bad, I'm sorry to change in between. This you take it as small r and this you take it as 2 small r. Okay, through how much area heat is entering? Pi small r square. Those who want to feel, yes, look, pi small r square. Pi small r square. Now, resistance of the orange one, length is L, thermal conductivity K2. Can you tell me through how much area heat is entering and through how much area heat is leaving? Man, this orange shaded portion, the total area is 4 pi r square because radius is 2r. So the area of the total one is pi into 2r square, which will be 4 pi r square, out of which you have to remove pi r square. So this portion is 4 pi r square minus pi r square, which is 3 pi r square. Okay. Hope everyone understood how I have chosen 3 pi r square. 3 pi r square. Okay. Now look. Now look. If you ever want to calculate the heat current, temperature difference divided by the equivalent resistance. So these two are in parallel. So 1 by R equivalent will be 1 by R1 plus 1 by R2. So 1 by R equivalent is going to be L by K1 pi R square. So K1 will be in the numerator. So pi small r square into K1 by L plus 3 pi small r square into K2 divided by L. So from here you can write the equivalent resistance or 1 by R equivalent. 1 by R equivalent to be what? Pi r square into K1 plus 3K2 divided by L. Now if I want the heat current flowing, it is going to be electric current, potential difference by resistance. Heat current, temperature difference by resistance. What is the temperature difference? See, this is at T1, this is at T2. So the temperature difference is T1 minus T2 divided by the R equivalent. And we already know the 1 by R equivalent. So write it. So it is going to be pi R square into K1 plus 3K2 into T1 minus T2 divided by L. Right? So this much amount of heat current will cross through this whole section. Will cross through this whole section. Okay, fine. Now, I want to replace the whole material with a single material. I want to replace the whole material with a single material. That's my aim. So, can you people see this color? Yes. Now, physical dimensions should be same, right? Physical dimension should be same. Physical dimension should be same. So this one maintained on T1 and T2 length L. Physical dimension should not change. That means the radius of this is 2r. Then from here, if I want to talk about the r equivalent, 1 by r equivalent, the k equivalent of it multiplied with the area, which is going to be 4 pi small r square divided by L. Now what you do is you just compare these two, this one and this one. So if you are going to be doing the comparison, can you tell me 4k equivalent is k1 plus 3k2. So what will be the k equivalent? It is going to be k1 plus 3k2 divided by 4. This is how you are going to be talking about the k equivalents. K equivalents. Super. One more question, but this question is a homework for you. This question is a homework for you because the class time gets stretched as I dig too deep into it. As I said, current electricity and this one are very, very, very similar. Okay. Is it mandatory that always we have to deal with rods only? No, right? Now, I'm giving you a question. I'm giving you a question. I am giving you a question. Look, it's a sphere. Okay. Look, man, if I am going to talk about inner radius of this sphere is A and the outer radius of this sphere is B, we have a sphere like this. So what I am doing is this whole inner surface is maintained at T1 temperature and the whole outer surface is maintained at T2 temperature. The whole inner one is maintained at T1 temperature and the whole outer one is maintained at T2 temperature. How the current is going to flow? How the heat current is going to flow? Obviously, the heat current is going to be flowing like this. The heat current will be flowing like this. So now, if you look at it, heat current is entering through 4 pi a square area and it is leaving through 4 pi b square area. That means you have a problem. You have a problem. Definitely you have to take elements and you have to do integration. You have to find it. Let us take the thermal conductivity of this one to be K. Find the heat current that is going to be crossing and find temperature of layer at r distance, at smaller distance. And I'm going to give one trick, man. Whenever you are going to have areas to be r square dependent, and if the radius is changing, in that r square part, you put a into b. Wherever you have r square involved, if you know two different radiuses, that is the smallest radius and the biggest radius, shortcut is going to be, I'm giving you shortcut for all questions where r square will be involved. Wherever r square will be involved, that r square in the final result is going to come out to be small radius to the bigger radius. Smaller radius to the bigger radius. This is a shortcut, but I want you to approach in a proper way. Proper way. Okay. Nice. Good. Then solve some questions. Come on. What I did previously was I have given the rods to be having same thickness L and L, But in this question, the thickness is different, D and 3D. Do it. It's D and 3D. Come on. We're almost there. Almost there, heat transfer will be completed. Almost there, heat transfer will be completed. Come on. Two materials having coefficients of thermal conductivity 3K and K and thickness D and 3D respectively are joined to form a slab as shown in the figure. The temperatures of the outer surfaces are theta 2 and theta 1 respectively. Theta 2 is greater than theta 1. The temperature at the interface, they are asking the junction temperature. They are asking the junction temperature. Let us take the junction temperature to be some theta. Right? How much our heat current will flow through this, same heat current should flow through that. So I am taking the heat current through this one to be H1. I am taking the heat current through this one to be some H2. So what is H1? H1 is going to be thermal conductivity 3K area into higher temperature minus lower temperature divided by the distance. Now what is H2? H2 is going to be thermal conductivity is K A theta minus theta 1 divided by 3D. Now H1 is going to be equal to what? H2. So when you equate, Ka by D is going to get cancelled out. You get 3 times theta 2 minus theta to be equal to theta minus theta 1 by 3. So you multiply this 3 also onto this side. So I am writing red color. I'm using red color and they have changed the saturation and all those things. As a result, I'm looking dark and fine. 9 theta 2 minus 9 theta is equal to theta minus theta 1. Super. So you are going to get 9 theta 2 plus theta 1 divided by 10 as theta. So which option? This option. Option A. Option A. Super Sanjay. Super. Okay. Do this. Do this. This is also a good question. Although it is from 2014 and many of those questions which are old ones, they are way better than the questions that are being asked these days. And one more thing what I have noticed is that old questions have been repeated. Old questions have been repeated. Repeated in the sense models have been repeated. 3 rods of copper, brass, steel are welded together to form a Y shape. Area of cross section of each of the rods is 4 cm square. End of copper is maintained at 100, whereas the ends of brass and steel are kept at 0 degrees. Okay. Let me draw that. Let me draw that Y shape, right? Let me draw the Y shape. Yes, Y shape. This is copper. Copper, one end is maintained at 100. And then we have brass and we have steel. Brass is at 0, steel is maintained at 0. Okay, good. Are kept the lengths of the copper brass are 46, 13 and 12. Forty-six, 13 and 12 centimeters. Now they are asking the rods are thermally insulated from surroundings except the ends. The conductivities they have given. Rate of heat flow through the copper. Rate of heat flow through the copper. Now look, somehow you need to find the junction temperature. If you can find the junction temperature, then what will happen? You can find the heat flow. Okay, let me just take this to be HC and this to be HB and this to be HS. How much hour is entering? Same has to leave. So HC should be equal to HB plus HS. Right? And you can see everything is in CGS. You put everything to be in CGS only. Now HC is going to be what? K, thermal conductivity of copper, which is 0.92. So 0.92 K A 100 minus T divided by the length. Length is how much? 46 is going to be 0.26 into A into T minus 0, which will be T, divided by its length, which is 13. And then you have 0.12 for steel into A into T divided by how much length? 12. So do the calculations. And the calculations are not that difficult, man. Why? See, and A are going to get cancelled out. And if you see, this is 0.02 kind of thing. This is also 0.02. This is going to be 0.01. So in that way, calculations are not difficult. Find out the temperature. Find out the temperature. I think the temperature will come out to be 70 as far as I remember. How much you are getting? Sanjay, what's the T value you got? What's the T value you got, Mr. Sanjay? So when I simplify, this is going to be 2 into 100 minus T. This is going to be simply 2T and this is going to be 1T. So you get 200 divided by 5T. Huh? Yes. 200 divided by 5T. So the T is going to come out to be 40, man. 40 degrees. Put 40 over here, then 100 minus 40 will be 60. You are getting, calculation part, I got something else, man, then divided by 46, 0.02. So 2, here also you'll have 2, there you'll have 1. Yes, my calculation is correct. Now you put the T value. When you put the T value, heat current through the copper is going to be 0.96 into 4 centimeter square into 100 minus 40 divided by 46, which is going to give you 0.02 into 4 into 60. 0.02 into 4 into 60 is 4.8. It's 4.8. Check your calculation, Mr. Sanjay. Check your calculations, Mr. Sanjay. Okay. What if we have 3 rods? Not 2 rods. What if we have 3 rods? We don't need to worry at all. We don't need to worry at all. Okay. 3 rods of identical cross-sectional lengths are made of 3 different materials of thermal conductivity K1, K2, K3 respectively. They are joined together at their ends to make a long rod. One end of the long rod is maintained at 100, other at 0. If the joints of the rod are at 70 and 20 in steady state, there is no loss of energy from the surface of the rod. The correct relationship between K1, K2 and K3 is the correct relationship. Like, heat current has to be same, man. H1 should be equal to H2 should be equal to H3, indicating K1 same area 100 minus 70, 30 divided by, what is the length, man? Lengths are made of 3 different materials. Okay, lengths are also same, it seems. L. K2 A temperature difference 50 divided by L is K3 A temperature difference 20 divided by L. So I can see that 3K1 is equal to 5K2 is equal to 2K3. From this ratio, you can easily find out the relation. As far as I remember, there was some typing mistake. I think this was not there. First of all, let us look at K1 to K3. K1 by K3 will be 2 by 3. Yes, 2 is to 3. And K1 is less than K3. That is also correct. So option A. If you look at K1 by K3 ratio, it is 2 by 3, clearly indicating K3 is more than K1. So option A is correct. Option A is correct. Okay. No matter how many rods they give, na, don't worry. Do this question. This is a good question. This is also a good question. Temperature difference of 120 degrees is maintained between the two ends of a uniform rod AB of length 2L. Okay. Another bent rod PQ of same cross section as AB and length 3L by 2 is connected across AB. In steady state, the temperature difference across PQ. Man, convert it into current electricity question. Convert it into current electricity question. That's it. Right? If there is L length, look, you take the thermal resistance to be L by Ka. R you take it to be L by Ka. So if the length is L by 2, then the resistance is R by 2. Here also length is L by 2, so resistance is R by 2. Here the total length is 3L by 2, so the resistance is 3R by 2. So I can convert this question into 1R by 2, and then we have R, and then we have 3R by 2 in parallel, and then we have R by 2. And we know that the temperature difference is 120. So TA, and this to be what? TB. So 3R by 2 and R in parallel is going to give you how much? 3R by 2 and R in parallel is going to be giving you how much? So the R equivalent of this is going to be R1 into R2. 3R by 2 into R divided by 3R by 2 plus R, which will result in 3R by 5. And then we have R by 2 and R by 2, which will be R plus 3R by 5, which is going to be 8R by 5. So what is the total resistance? We have the total resistance to be 8R by 5. Total resistance is 8R by 5. Okay, done. If you know the total resistance, how much heat current is going to flow down? The heat current that is going to flow is going to be temperature difference divided by the total resistance. Divided by the total resistance. Temperature difference 120 divided by total resistance 8R by 5. So H is going to be 120 into 5 divided by 8R. Okay, this is clear. No, Madhan, I am not Tamil, I speak Telugu. Okay, my mother tongue is Telugu. This is P, this is Q, right? So if you want the potential difference, or sorry, temperature difference across PQ, it is this resistance multiplied with the current that is going to flow, right? How much is this resistance? 3R by 5. So the temperature difference across PQ is going to be the heat current multiplied with the resistance. So 120 into 5 divided by 8R into 3R by 5. RR 5 5. 4 2s 30 90. No. 4 2s 30 15 45. So the answer is 45. 45. So this is a good question. This is a good question. Combination of current electricity with you can say heat transfer, that is conduction part. Super. If you love the content that is being delivered, please hit the like button. Please hit the like button. That's all we demand. That's all we request you people. That's all we need. That's the support. Okay, already this question has been done to you. Answer is K1 plus 3K2 by 4. Already I have done this. Ninga Tamila. No, ma, I'm not. Hi, 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 Rupa. Okay. This is the last part of heat transfer. This is the last part of heat transfer. Rate of formation of ice. Rate of formation of ice. Okay. See, real lakes, a real lake is going to have its area of cross section changing. Real lake, its bottom is going to be looking something like this. The bottom is going to look something like this. And we know in foreign countries, ice is going to get formed. Now I want to talk about rate of formation of that ice. I want to talk about rate of formation of that ice. So for that, what I will do is I'll just take an ideal lake. What is an ideal lake? Ideal lake is one such thing. Ideal lake is one such thing whose area of cross section is same. Whose area of cross section is same throughout. Just a second. So I have come to the lake at some time t. By then some ice has already got formed. By then some ice has already got formed. So this much ice has already got formed. This much ice has already got formed. I have come to the lake at some time t, and the surroundings are at minus t degrees Celsius, and some x thick of ice has already got formed. Now in the next dt time, some more ice gets formed, right? Some more ice gets formed. That ice that is going to get formed, let us take, is this section is converting from water to ice. This section is converting from water to ice. Let us take the thickness that is going to get converted to is dx. Now when water gets converted to ice, it releases heat, right? And where the conversion takes place? Obviously at 0 degrees. So whatever the heat is produced, that heat should be crossing the ice. Why it should be crossing the ice? Because how much our heat is produced, if that is taken by heat, then here dx thick ice gets formed. As the ice is going to retain that heat, then dx thick of ice should melt, right? But that is not happening. Continuously the thickness of ice is increasing. If continuously the thickness of ice is going to be increasing, then how much our heat is produced here should be conducted through ice and thrown to the surroundings. First of all, how much amount of heat gets produced, how much ever amount of mass is getting converted from water to ice. So density multiplied with volume. I am taking the area of cross section of the lake to be A, and the thickness of it is dx. So this much. This much. Okay, this much heat is getting produced. That should be conducted through the ice and thrown to the surroundings. So what is dq by dt then? Dq by dt is going to be the conductivity, thermal conductivity of ice into the area of cross section. Obviously, one end is at 0, other end is at minus T. So, from higher temperature to lower temperature, which is going to be 0 minus of minus T divided by X. So, what is the dq value? Dq is rho A dx, rho A dx into L divided by dt is going to be KAT by X. Now, what will happen? A and A gets cancelled out, right? So, I can write the dt as rho L by KT into X dx. Now, by the time you have gone to the lake, let's say at time t is equal to 0, when you went to the lake, already there is some x1 thickness. So in time t, let's take, it became some x2 thickness. Now, when you do the integration, what are you going to get? Rho L by 2kt into x2 square minus x1 square. So you can say that the time taken is proportional to x2 square minus x1 square. You can say this. What is this t? Time taken for thickness of ice, to go from x1 to x2. From x1 thickness to become x2 thickness, whatever the time is taken is the one which is mentioned in the formula. Is that clear, everyone? With this, we are done with heat transfer. Is everyone clear with what I have done? Is everyone clear with what I have done? I would like to give you one small question. If you people say clear, if you love the content, please press the like button. Come on. Those who are there in the live, tell me, are you clear till here? Are you clear till here? I know there will be a lag, so I'm just giving you a question. Meanwhile, I'll see your response. So the question is, first 5 centimeters of ice got formed in 10 minutes. Find time taken to form next 10 centimeters, no, not 10, yes, next 10 centimeters of ice. First 5 centimeters, it has taken 10 minutes, it seems. Next 10 centimeters of ice, next 10 centimeters, how much time it is going to take? How much time it is going to take? Right? So my legs are paining, man. You keep trying this question. I'll just give you a break. As I was continuously standing. I'll just give you a break of some 10 minutes. Now the time is 7:18. We'll be back at 7:29. We'll be back at 7:29. Solve that question. Okay, I've come back. Look, man, from 0 to become 5. So that I'll take it as T1. I'll take it as T1 is going to be like T1 by T2 is what I'm talking about. From x1 thickness to x2 thickness. That means from 0 to 5. So 5 square minus 0 square divided by. Now what they are saying, for the next 10 centimeters, that means from 5 centimeters it should become 15. So 15 square minus 5 square. So T1 is given as how much? T1 is given as 10 minutes. So 10 divided by T2 is going to be 25. 15 square is 225. 225 minus 25 is going to be how much? 200. So from here you are going to get 10 by T2 to be equal to 1 by 8. So the T2 is going to be 80. So if the first 5 minutes is formed in 10 minutes, next 10 centimeters will be formed in 80 minutes. You can clearly see that the rate of formation of ice is slowing down. So what happens in those cold countries is that rate of formation of ice, as it is going to be slowing down. So first, let's say first 2 centimeters of ice has taken, let's say, some 1 month. Next 2 centimeters might take some 2 months. As a result, what will happen? The season gets changed. So from winter, it will become summer. So never the whole lake is going to get frozen. Never the whole lake is going to get frozen. Sir, once more, please. Okay, fine. Look, let us look at this formula. What is this formula saying? Time is directly proportional to x2 square minus x1 square. What is x1? The initial thickness. So from x1 thickness to go to x2 thickness, this much time it takes. Right? Now, to go from 0 thickness to 5 centimeters of thickness, it has taken 10 minutes. Now, to go from 5 centimeters thickness to 15 centimeters, because I am talking about next 10 centimeters of ice. So from 5, it should go to 15, then the thickness will be increasing by 10 centimeters. So to go from 5 to 15, how much time it takes is what we are calculating. Clear, Mr. Gaming Tamil DK. Okay, now look, let us talk about convection. See, as I have put both of them to be in centimeters, na? So here centimeter square, here also centimeter square, they get cancelled out. So whenever you are talking about ratios, whether you put them in centimeters or in meters, it doesn't matter. It doesn't matter. It doesn't matter. Okay. So what is this convection? See, convection is always going to be like you heat some medium. As the medium gets heated, its density is going to change. As a result, it will change its location. It will change its location. For example, for example, uh, let us take, we have particles of air. We have particles of air. Now, what I am going to do is, I'll just heat the layers with a burner. With a burner, I am heating the air. Then those particles which are going to be close to the flame, they absorb the heat. They become hot. When they are going to be becoming hot, so this section's density decreases. So what will happen? The lower density ones should be at the top and the higher density ones should be at the bottom. As a result, this one will try to rise up. So there is a space which is getting created when this is going to go up, there is a space. So the air from the surroundings will try to come and fill that space. So what is happening? The hot particles, the hot particles are rising up. They're rising up. When they rise up, they carry heat along with them. They carry heat along with them. So if you are going to look at the natural convection, in natural convection, heat always goes from bottom to top. As I said, convection is going to have some basic theory based questions. You won't have any numerical questions because the convection, there is no standard formula that is given. Okay. Now, let me just explain some few more, like land breeze and sea breeze, right? Let us talk about during daytime. During daytime, which one is going to be more hot, the land or the sea? We know that land gets heated up faster and the sea is going to get heated up slower, right? Water has higher specific heat, so it takes some time for it to get heated up, but land gets heated up fast. So when I'm going to talk about the air molecules, that are going to be on the ground, they get heated up fast. As a result, their density is going to be decreasing. If the density is going to be decreasing, then what should happen? So this section of air, as its density will be decreasing, they rise up, which will try to be filled by the air from the surroundings. So what will happen? You see that the breeze or the wind is going to be from the sea to the land. That's why we call it as sea breeze. So we will have sea breeze during the daytime because land gets heated up fast. Land gets heated up faster. And what happens during the night time? So when I am going to talk about during the night times, during the night time, obviously the one which is going to get heated up fast is the one which is going to get cooled down fast. The one which is going to get heated up faster is the one which is going to get cooled down faster. So during night time, this is going to be cold and this is going to be relatively hot. As a result, so you can say the air molecules over here are going to be getting heated a bit. They rise up, which will try to be filled by the particles from the land. So then you are going to have land breeze. Those who are in the coastal regions will clearly feel this. If you next time when you ever visit a beach during daytime, you can clearly feel that from wind from the ocean or the sea is going to be going on to the land, and during night time from the land onto the sea. Next, one more, just one more. Look, we have something like this. There is a liquid filled throughout. There is a liquid which is filled throughout. And what I will try to do is, I'll just try to heat up on one side. So which side you want to heat, it's up to you. Like, as there will be a lag, I will only pick. For example, I'll take a burner and I will be heating the right side one. How the liquid will move inside. If I am heating on the right side, how the liquid is going to move. Look, this portion gets heated up. As a result, its density will decrease. As a result, that liquid will try to go up, which will be tried to be filled by the liquid from the side. As a result, what you will have? You will have the liquid moving in anti-clockwise direction. So, if you are going to be heating the very same thing on this side, then the liquid here will go up, which will be filled by the liquid from the side. Then there will be clockwise movement. And there will be clockwise movement. So these are the things which you people should know from convection. That's it, right? And now, generally, let's say during Pongal time, we are going to do bogi, right? Like what we are going to do is we are going to put some stack of wood and there will be a fire. We will be standing in front of that bonfire or whatever you want to call it. Then you feel certain warmth, right? Certain heat you feel when you are standing away from the fire. So that heat what you feel, majority of it is due to what? Is a question which I am asking to you. When there is a fire in front of you, when you stand in front of the fire, you feel some heat. That heat is because of conduction or convection or radiation. See, first of all, fire I have fire and I am standing here. When I am going to be standing here, if you talk about the heat flow through for convection, heat flow is from bottom to the top. It goes. So the heat what you feel is definitely not because of convection. Now we have air. Right? So the air molecules are going to be transferring some amount of heat to you, and that is going to be conduction, but air molecules are not as closely packed as we see in solids. So the amount of conduction is also going to be less. So the amount of heat you feel, if it is very less due to convection and very less due to conduction and no at all from the convection, then automatically who is the third category? Radiation. So majority of the heat you feel when you stand in front of the flame is due to radiation. Majority of heat we feel is due to radiation. I am not ignoring conduction, but the amount of heat transfer due to conduction is very small. Convection, not at all. Radiation, yes, majority is due to radiation. Gaming, sir. Okay. I'm coming, man. I'm coming, Mr. Sanjay. Let us go for radiation. And as I already promised to you, I am not going to be dealing with radiation in deep, because in last 10 years, if you are going to see also, I don't remember a single question on radiation in JEE mains. JEE Advanced, yes, we have questions. So when we are preparing, when we make you prepare for JEE Advanced, that's when I'll focus more on radiation. As of now, I'll just give you the basics. As of now, I'll give you the basics. Working hard. Thank you for recognizing. So working hard, I said, thank you, sir, for the lectures. You're welcome. Now, I'll directly talk about Stephen's law. I'll directly talk about Stephen's law. What this fellow has said. He said that a black body, which is at certain temperature, is going to be radiating out some heat. And for that, for you to understand what he has completely given, you need to know about something called as emissive power. Emissive power represented with capital E. Emissive power represented with capital E. So what is that emissive power? The amount of heat radiated per unit time per unit area. dq by dt per unit area is the emissive power, man. Right? So what Stephen said, I have a black body, right? I have a black body and the temperature of that black body is T. Then Stephen said that the emissive power of it is directly proportional to T to the power 4. Emissive power. What is emissive power? The amount of heat coming out per unit time, per unit area from this body is emissive power. Okay, now look, if I am going to be replacing that proportionality with a constant, we replace it with a constant called sigma, and that is called Stephen's constant. And that is called Stephen's constant, and that sigma is 5.67 into 10 to the power minus 8. What will be the units, man? This is joules per second per meter square per Kelvin to the power 4. And one more thing, this T should be put in absolute temperature. Now look, this is for black body. Now, am I a black body? No, I am not a black body. Are you a perfect black body? No, you are not a black body. But we have temperature and we radiate out energy. So, while solving numericals, okay, fine. While solving numericals, while solving numerical questions for other bodies, they give something called emissivity. Represented with the letter small e. So if it is some body, like if it is a normal body, not the black body, then the emissive power that is going to be coming out, then the emissive power that is going to be for this one, which is having T temperature, the emissive power is given by E times sigma T to the power 4. See, based on the numericals, I am giving you this. If you refer to different books, there will be something called as ER. So the way it is defined is different in different books. But as I said, when you look at the normal competitive examinations, they are going to give something called as small e. Right? If you talk about normal bodies, what are normal bodies? You, me, this building, this screen, right? The camera or the pen, everything is normal body and there will be some emissivity associated with it. Okay. Now that E can be written as what? dq by dt by A is emissivity of that body into this. So how much heat is radiated per unit time, or the power, or the power rate at which heat is radiated out is this much. Okay, fine, nice, good. Everything is good. Man, my body has certain temperature and I am put in atmosphere, and the atmosphere also has certain temperature or not. Anything which is going to have temperature is going to radiate heat. That means the surroundings wherever I am there, the surroundings where I am there is having temperature. So the surroundings radiate heat. That heat will fall on my body. Some portion get absorbed. So the net heat given out by me is not simply the heat. Whatever is radiated by me, I also absorb something. So if I am going to talk about a body whose temperature is T, which is kept in some surrounding temperature T naught, the net heat given away, net heat given away, net heat given away is the heat it has radiated out minus the heat it absorbs. How much it is going to be absorbing? Actually, there is a story for that. I have to prove it, but I'm not proving it. I'm just giving you this. I can simply say this, and it is going to be this one. Okay. For some reason, my brain is not accepting me to just give one formula because it's not a law, also, right? It's not a law, also. Me writing like that, I'm not getting the satisfaction of teaching. Shall I explain how this has come? Man, that's the problem with me. I love to give lot of details. If the temperature of this one was T naught, if the temperature of this one was T naught and surroundings is also T naught, will the temperature of this body change? No. Thermal equilibrium is there. So net heat flow should be what? 0. That means when the temperature of this one is T naught, how much it radiates? E sigma A T naught to the power 4. If the temperature of this one second, let it go off. If the temperature of this one is T naught, E sigma A T naught to the power 4 should be radiated out. And I know that as the temperature of this body is not going to be changing, then how much it should absorb? Exactly the same amount. So if the temperature of this body is T naught, and if this is also T naught, there is thermal equilibrium, net exchange of heat will be 0. So how much ever is radiated, same will be absorbed. So when the surroundings are at T naught temperature, how much it is absorbing? E sigma A T naught to the power 4. This much is absorbing. That much is absorbed. E sigma A T naught to the power 4. Now if the temperature of the body changes, but the surroundings are at T naught only, so how much our heat it will radiate, it is remaining the same. So how much will be absorbed should also remain the same. So always it will absorb how much? It will absorb this much. Now I think logically I have made it clear to everyone. So this much amount of heat. So net heat radiated out per second. Net net, what is this? Why it is so thick? Net heat net heat, I won't say, net heat given away per second is going to be E sigma A T to the power 4 minus T naught to the power 4. That's it, man. That's all you need to know. So can we get this notes as PDF, please? Tell me. I'm new to here now itself. Gaming Tamil DK. All of this will be in the description below. After the class, I'm going to share the PDF. They will upload it in a link. So when you go down in the description, you will find something called as Jungle Book. In the Jungle Book, this PDF will be available. Okay. Now, there is something called solar constant. There is something called solar constant. So what is that solar constant? I'll represent with some small s. Man, sun is treated to be a black body. Sun is treated to be a black body. Take it this to be sun. And what Earth does, let us say Earth is going in an orbit around this sun. Like, okay, better take this to be sun. Let me go one at a time. Let's take the temperature of the sun to be T, and this is sun. And let us take Earth to go around the sun with an average mean radius of this much. And where is Earth? Somewhere over here. Obviously, when compared with sun, Earth is going to be very small. This is the Earth. Now, because of the temperature of the sun, what the sun does, it just radiates energy. It just radiates energy. And what is the emissivity of sun? As I said, sun is treated as a black body. Emissivity of sun is going to be 1. So the rate at which heat is emitted per unit time is going to be sigma area of the sun into T to the power 4. I will take the radius of the sun to be capital R. Then it is going to be 4 pi capital R square into T to the power 4. This much power is given by the sun. This much is the power that is being thrown in all the directions. Now, let me take the mean radius of Earth around the sun to be smaller. So, whatever the energy is given by the sun is going to be distributed equally on the sphere or not. So, what is the intensity that is going to be reaching this sphere? So, the intensity that is going to be reaching the sphere is the power radiated by sun per unit area. And this intensity is only called as solar constant. Is only called as solar constant. Yes. So what is that S? It is 4 pi sigma capital R square into T to the power 4 divided by 4 pi small r square. 4 pi gets cancelled out. So the solar constant is sigma r square T to the power 4 divided by small r square. Okay. Do you know, with the help of this one, we can calculate the temperature of sun. Because I am staying on Earth, I will find out I'll find out how much energy is reaching per unit area per unit time. All I do is I put a detector to the sun rays normally. Then I'll get the intensity that is reaching. That means I know the S, I know the sigma, I know the mean radius, and I know the radius of sun also. So from here, t to the power 4 is s into small r square, s into small r square divided by sigma r capital R square. So the t is going to be s into small r square by sigma capital R square to the power 1 by 4. We can easily calculate, and that solar constant, as far as I remember, I'm bad with memory, is 1367 watt per meter square per second. Watt per meter square. Why? Solar constant is nothing but intensity, man. What is intensity? Energy reaching per unit area per unit time. That only is named as solar constant because I am talking about Earth and the energy reaching from sun to Earth. That's why I call it as solar constant. Now, did you understand how people measure the temperature of sun without even going and taking a thermometer along with them to the sun? In this way. You know, yes, the intensity of sunlight rays. Intensity of sunlight rays, you know the radius, the mean radius or the mean distance between sun and the earth. You know the sigma, you know the radius of sun. From there, khatam, done. Okay, now look, take a small question on this. Keep in mind, when I'm talking about Stephen's law, I was talking about the temperature, and that temperature is absolute temperature. You have to put it in terms of Kelvin. You have to definitely put it in terms of Kelvin. So find the ratio of emissive power at temperature 27. So our T1 is 273 plus 27, which is going to be 300 Kelvin. And T2 is 127 degrees plus 273, which is going to be 400 Kelvin. So 300 Kelvin and 400 Kelvin. Now if I am going to talk about ratio of emissivities, E1 by E2 obviously will be T1 by T2 to the power 4. 1 second, you might get confused. I'll write capital E1 because they are talking about emissive powers. So simply it is going to be 3 by 4 to the power 4, which is going to be how much? 81 is to 256. 81 is to 256. Okay. Next. If the temperature of sun were to increase from T to 2T and its radius from capital R to 2R, ratio of power radiated, not the emissive power. They are talking about power. Power is going to be what? Rate of heat radiated, dq by dt. And what is dq by dt? As it is sun, you can take the emissivity as 1. So sigma 4 pi r square, sigma a t to the power 4. So the power is directly proportional to r square and t to the power 4. Now, if you talk about the ratio, P1 by P2 is going to be R1 by R2 to the power 2 and T1 by T2 to the power 4. So what is R1 by R2? 1 by 2. So the ratio of the powers emitted 1 by 2 square. And what happened to the temperature? From T, it became 2T to the power 4. So this is 1 by 4 and 16, 64. So you can say P2 is going to be 64 times P1. So answer is A. Answer is A. Okay. Now look. This fellow was so much interested in checking. See, a body which is having temperature T, it is giving away radiation, heat. It is giving away radiation. So Wien was like, okay man, at a particular temperature, A body is giving away radiation. I'll trap that whole radiation and I'll find out, is it preferring any one particular wavelength more. So what he did, he did spectral emissive power versus wavelength. So he was talking about, when I say spectral emissive power, it is nothing but he's just measuring like one particular wavelength how much energy, other particular wavelength how much energy, other particular wavelength how much energy. For example, lambda 1 how much energy is there, lambda 2 how much energy is there, lambda 3 how much energy is there. Like that he trapped the radiation radiated by the body. For example, if I am there, I have certain temperature, I have radiated out that entire radiation he trapped, and he checked how much wavelength, sorry, he trapped the entire radiation and he measured this particular wavelength has how much energy. Then he plotted the graph. And one interesting thing is that he found out that a body which is at some temperature T is going to radiate different wavelengths of energies, out of which one particular wavelength was having more energy radiated. So that means if I am the body at a particular temperature, when I am radiating out, I'll send all wavelengths of energies, but I prefer one particular wavelength more. I love that wavelength. And what he found out is that that wavelength which is preferred multiplied with the temperature is constant, and that is going to be called as Wein's constant. So lambda m into T is some 2.89 into 10 to the power minus 3 meter Kelvin. Stefan said that a body which is at T temperature radiates out energy. Then what Wien said, a body which radiated out energy at a particular temperature prefers one particular wavelength more. Prefers one particular wavelength more. When compared with other wavelengths, this wavelength energy will be more. Okay. That's so now you can clearly see that as the temperature increases, the wavelength it prefers to send out more decreases. So they'll plot some graph. And they are going to ask you the relation between the temperatures. So spectral emissive power versus wavelength. Let us say we have one particular thing like this, and we have one particular thing like this. The temperature of this one is T1 and the temperature of this one is T2. Please relate, like find the inequality between T1 and T2. Find inequality between T1 and T2. It's very simple. If you are going to talk about the lambda m1 and this is lambda m2, we know that lambda m into T is constant. So as lambda m2 is more than lambda m1, it's very clear that T1 should be greater than T2 because lambda into T has to be constant. Lambda into T has to be constant. Take a small question. Lambda into T is constant, right? A black body at 1500 Kelvin emits maximum energy of wavelength 2200. If the sun emits maximum energy wavelength this much, calculate. Man, lambda into T is constant. So what is the lambda? 2200. It prefers, so a black body which is at 1500 Kelvin prefers this wavelength more. So don't get confused. It prefers this wavelength more. So is it emitting other wavelength energies? Yes. A body which is at T temperature radiates out lot of energy, right? In that energy, you will have all wavelengths, but it prefers one particular wavelength more. That's it. That is what is given by Wayne. Okay, 220 2200 into 1500 is going to be 5500 into the temperature. So the temperature is going to be 22 into 1500 divided by 55. So the temperature is 2 by 5 into 1500. So you can say this to be 300. So the temperature of the sun is 600 Kelvin from the data that is given. If the wavelength increases, temperature has to decrease. So if this is 1500, definitely the temperature of the sun has to be less than 1500. Okay, with this, we are done. We are done with the total thermal physics except KTG and thermodynamics. So next week is KTG and thermodynamics. If you have anything to ask, you can ask. If you love the content, whatever has been done to you, please like the video. That's the only request we have. We don't demand any money from you, right? We are not forcing you to do anything. You haven't paid lakhs, nothing. If you have to motivate us, the only way you are going to be motivating us is through some positive comments and through likes. That's the only thing, right? If you have anything to ask, you can ask me. Otherwise, I'll leave the session. Like, I don't want to waste any time. Okay, then. Bye. Good night. Keep working hard.